Now we will study the main assumptions or postulates of conventional transition state theory. Okay, there are several postulates. Let us understand one by one. The first postulate or assumption of transition state theory is the molecular species, okay, that have surmounted, that is, it has reached, okay, the call. Okay, I already told you what is call. It is the peak of our potential energy diagram. So molecular systems that has reached or surmounted the call in the direction of products cannot turn back and form reactant molecules again. Okay, they cannot turn back and form reactant molecules again. What is the meaning of this assumption? First, let me read the assumption again. Molecular species that have surmounted the call. What molecular species I am talking about? It is nothing but the activated complex that are formed at the call. Okay, that activated complex, once it is formed, it has no other option other than forming the product. Okay, it can move only in the direction of formation of product. It cannot revert back or turn back and form the reactant molecules again. So if I have again draw the potential energy diagram, potential energy, and this is the reaction coordinate. This is how the potential energy diagram looks. So this is the reactants, this is the product side, so this is the activated complex represented by the symbol X dagger. So when the reactant molecules after collision has formed the activated complex, okay, once this species is formed, okay, when this species is formed here, this species can only move in the forward direction. Okay, it can only move in the forward direction. It can only roll down to form the product. It cannot roll back to form the reactant. So this is not allowed. So there is only one direction here. The reactant will be converted to activated complex. The activated complex can only move in the forward direction. It cannot form the reactant again. So this this process where reactant is forming the activated complex, that is a process uh, taking place only in forward direction. So this is not a reversible process. Reactant may form the activated complex, but the activated complex may not revert back, cannot revert back and form the reactant. So this process takes place only in forward direction. So there is no equilibrium between the reactant and the activated complex. You know that a equilibrium is established only if the reaction is reversible, but this process is not reversible. The reactant can form the activated complex, but the activated complex cannot again form the reactant. So this process is not reversible in nature, and therefore there is no equilibrium established between the reactant and the activated complex. So this is an assumption made by the transition state theory. The second assumption of the transition state theory is, okay, the energy distribution among the reactant molecules, okay, the energy distribution among the reactant molecules is in accordance with the Maxwell-Boltzmann's distribution. Further, this is important. Further, it is assumed that even when the whole system, even when the entire system is not at equilibrium, when the entire system is not at equilibrium, still the concentration of the activated complex, the concentration of the activated complex that are becoming products, okay, is calculated or can be calculated by equilibrium theory. That is, the concentration of activated complex is calculated as if there is a statistical equilibrium between the reactants and the activated complex. Okay, a very lengthy assumption, but the meaning is very simple. Okay, so we have a large number of reactant molecules in the reaction mixture. Okay, you don't carry out a reaction with one molecule of A and one molecule of B. Okay, so whenever you are carrying a reaction, you mix a large amount of reactants of the order of 10 to the power 20 molecules or 10 to the power 23 molecules, okay, or greater than that. So when you have a large number of reactant molecules, okay, you know that the energy of each reactant molecule will not be the same. Okay, the energy is distributed among the reactant molecules in different way, and how that energy is distributed is answered by the second postulate. So according to the second postulate of transition state theory, the energy distribution among the reactant molecules is in accordance with the Maxwell-Boltzmann distribution. You have different types of distribution: Maxwell-Boltzmann distribution, Fermi-Dirac distribution, Bose-Einstein distribution. So here they have assumed that the energy of the reactant molecules is distributed in accordance with Maxwell-Boltzmann distribution. Further, this is very important. Okay, I already told you there is no equilibrium between the reactant and the activated complex, but still, in order to calculate the concentration of the activated complex, we use the equilibrium theory to calculate the concentration of the activated complex. So though there is no equilibrium between the reactant and the activated complex, while calculating the concentration of the activated complex, it is assumed that there is some sort of equilibrium, which in fact does not exist, but still we are using the equilibrium theory to find out the concentration of activated complex that is formed and which is ready to form the product. Why? Because greater the concentration of the activated complex, greater is the chance of the formation of the product, which in turn would result in the increase in the rate of the reaction. So greater the concentration of the activated complex means greater would be the chance of formation of product, and which means greater should be the rate of the reaction. So the determination of the concentration of activated complex is a very important exercise in transition state theory. So how to calculate the concentration of activated complex is very important, and that is given by the second postulate, that is, even though there is no equilibrium between the reactant molecule and the activated complex as per the first postulate, but yet in order to calculate the concentration of the activated complex, it is assumed, okay, that there is some sort of equilibrium which actually does not exist. So we consider that equilibrium only for calculating the activated complex concentration and for no other else, and for all other discussion it is assumed that there is no equilibrium between reactant and the activated complex. So this is the second postulate of activated complex theory. The third postulate, okay, which I will only state here, we will understand the meaning or the significance of the postulate in the next class, when we will go into the mathematical details of this theory. Okay, the third assumption of this theory is it is possible or it is permissible, okay, it is possible or it is allowed to separate the motion of the system over the call, what is called, okay, that I already told you, the barrier of the potential energy diagram. So it is permissible to separate the motion of the system. When I say system, it is actually the activated complex, okay, motion of the system over the call from other motions, associated with the activated complex. Okay, what is the exact meaning of this? I will explain in the next class. Here I will explain briefly. Say for example, this is the reaction AB plus CD. Okay, I will take some complex structures. Okay, AB plus CD, E. Okay, giving product. So the final product is BD plus AC. Okay, F, I will take F. So A, E, F. Okay, some structure. Okay, so this is the reaction. So here the activated complex has to pass through a state something like this. Okay, the bond between A and D. Okay, sorry, here the bond between A and B is broken. Here the bond between C and D should be broken, and a bond, okay, I will make it with this is very complicated, this will lead to a lot of confusion. I will give a very simple example. Okay, so A B plus C B E F giving, okay, just take B, okay, giving B C D F plus E. Okay, so here the bond between B and C is formed and the bond between C and D is broken. So this reaction will pass through a state called as transition state, where an activated complex of structure something like this, bond between B and C is partially formed, whereas the bond between C and D is completely broken. Okay, so you have D F. Okay, here C necessarily is not carbon, some element, okay, some atom which is not carbon. Okay, so the activated complex has some sort of structure where the bond between B and C is not completely formed and the bond between C and D is not completely broken, and this finally forms the product. And for the formation of the product, the breakage of which bond is very important? The breakage of CE bond is very important. So the vibration associated with this CE bond is very important, and this molecule, being a very complex molecule, it can perform different types of motion. It has rotational motion and it has even several vibrational degrees of freedom. Okay, there are in fact 3n-5 or 3n-6 vibrational degrees of freedom, depending on whether the molecule is linear molecule or non-linear molecule, etc. Okay, so there are a lot of vibrational degrees of freedom. Now what this postulate tells is it is possible to separate the one particular important vibrational degree of freedom, which is the vibrational degree of freedom related to this particular bond, okay, from other motions, that is from other degrees of freedom which is associated with the activated complex. So the degree of freedom related to this particular vibration can be mathematically separated from the remaining degrees of freedom associated with this molecule. What is the meaning, exact meaning of this, we will discuss in greater detail, okay, when we go into the deeper understanding of transition state theory. Okay, so just remember what is the postulate or assumption. The fourth assumption of transition state theory is a chemical reaction can be satisfactorily explained, okay, or treated in terms of classical motion of the species over the barrier, comma, quantum effects being ignored. Okay, remember, for molecular species, okay, it is in fact the quantum mechanics which gives correct result than compared to classical mechanics. But here they postulate that, or they assume that the chemical reaction between the two molecules, okay, can be satisfactorily treated or explained in terms of classical motion of the species over the barrier, okay, quantum effects being ignored. What is the meaning of this? Let us try to understand. So again I will draw the potential energy diagram versus reaction coordinate. Okay, this is how a potential energy diagram generally looks. So this is the reactant, this is the product, and this is the activated complex. So a reactant molecule, okay, it slowly climbs this hill, and it forms an activated complex, and this activated complex will roll down and form the final product. So the motion of this molecule, okay, the molecule initially it's reactant. When it reaches this particular stage, it has reached a transition state where the species is an activated complex. Okay, further the motion of the species along this potential energy diagram, and finally when it reaches here, it has reached the product state. So the motion of the species above this potential energy diagram, okay, so this motion, okay, is assumed to be a classical motion. It means it follows the rules of classical mechanics. Okay, strictly speaking, the motion of the molecule along this barrier should be treated by using the rules of quantum mechanics, but here they assume that, okay, we get a satisfactory result even by considering the classical motion of the species over the barrier, ignoring quantum effects. Okay, what does this quantum effects do? According to classical theory, reactants, suppose the reactants has to get converted into product, it has no other way other than crossing this barrier and finally forming the product. There is no shortcut method for the reactant to form product. It has to climb this barrier, form the activated complex, which rolls down to form the product. This is called, what is the classical theory expects. If I want to reach from here to here, the only one way that is possible is to climb the hill, pass to the other side. That is the classical idea. Whereas according to quantum theory, if I apply the Schrodinger wave equation to this system and solve the Schrodinger wave equation, it gives a very important result which is called as tunneling effect. So what does this tunneling effect do is, okay, the reactant molecule, even though it has not gathered enough energy to overcome this barrier, there is a possibility or probability that the molecules, even without achieving that minimum energy, has a probability to form the product. Okay, that phenomenon is called as tunneling effect. So the reactant molecule, due to collision, it has gathered some energy and it has reached here, which is not, definitely not the maximum energy. So this is not the transition state, or this is not the structure of an activated complex. So according to classical theory, if the molecule has attained this much energy, it is no way eligible for forming the product. In order to form the product, the molecule has to gain more energy, more and more energy by collision. It has to reach the top of this barrier. Until and unless it reaches the top of the barrier, it cannot form the product. This is the classical picture. But according to quantum theory, if the molecule has attained energy corresponding to here, what I have shown here, there is a probability that even this molecule, without crossing the barrier, can form the product. So there is some sort of tunneling that happens within this barrier, okay, and the molecule will reaches here, which will roll to form the final product. So without reaching this maximum energy state, without formation of the activated complex, this molecule will tunnel through the barrier and form the product. So this type of results we get from quantum mechanics if we apply quantum mechanics. So quantum mechanics allows the possibility of tunneling, but here they are assuming that such complicated theories need not be applied. Even the classical motion of the particle through the barrier is sufficient to get desirable or appreciable result. Okay, so this is the meaning of the fourth assumption. The fifth assumption, which I have stated already, the rate of a chemical reaction is directly proportional to the concentration of the activated complex. Okay, so the rate is directly proportional to concentration of the activated complex that is formed, okay, which is ready to form the final product. This I have explained already. Why? Because once the activated complex is formed, it cannot roll back to form the reactant again. There is one way, that is to move in the forward direction, that is to roll down and form the product. So greater the concentration of activated complex formed, it implies greater is the concentration of the product that is formed, which implies greater is the rate of the chemical reaction. So the rate of the chemical reaction is directly proportional to the concentration of the activated complex. So finding out the concentration of activated complex is a very important exercise in transition state theory. And how to calculate the concentration of the activated complex and what are the exact meaning of these assumptions, we will study in the next class. Okay, there are two approaches for transition state theory. The mathematical treatment of transition state theory can be either done by using statistical mechanics, which is called a statistical mechanical treatment of transition state theory. The other way of discussing the transition state theory is using the classical thermodynamics, so which is called as a thermodynamical or classical thermodynamical treatment of activated complex theory or transition state theory. So in the next classes we will discuss about the statistical mechanical treatment and the classical thermodynamic treatment of activated complex theory or transition state theory. So with this I conclude today's class. We will continue with the statistical thermodynamics and classical thermodynamics treatment of transition state theory. Thank you.